And let me just try to share something on the screen to give you some idea of what it is. So let me know if you are able to view the screen and
Yes, sir,
somebody.
it's visible. The
So what?
syllabus.
Okay,
Yes,
great,
sir.
great. Thank you, thank you. So guys, with this basic introduction of mine, let's just again, let me just again welcome you. So this page basically gives you most of the idea. Total marks assigned to this course is 100, although this will be converted to your credits ultimately. Total duration of hours assigned is 60 hours, out of which 45 hours for lecture, which is what we are doing right now, and 15 hours for tutorial. These are the approximate numbers. Every semester we have some different, let's say, distribution depending on the number of weeks which we'll get. Now, the objective of the course is pretty clear. The primary objective of the course, people are waiting in the lobby, and unfortunately, this is something which is bugging me for the time being. So, Archana, I don't think I can do much about it because this person is going and admitting Palak. I'm sorry. Okay, going back. So, the course is divided into four major or broad units. First unit is what we call as the linear vector space, and this is the unit with which we are going to start this syllabus. Unit 2 is about theory of probability and statistics. 3 is about complex analysis, and unit 4 is about group theory. Number of lectures assigned broadly are also written. So you understand slightly the weightage of the units on the basis of the number of lectures assigned here. We know that you have done part of the vector space in your quantum mechanics class. We know that you have done complex analysis, surely. Part of the group theory is also taught at the undergraduate level, but we have to just see why this kind of course is there. I mean, I will just tell you soon that why do we have those 4 units. Suggested readings. 3 books are mentioned here. Mathematical Physics by V. Balakrishnan. The first one is an excellent text. This came later. I mean, you look at it 2018, but it is an excellent text. At times, it won't cover the entire syllabus. Mathematical Methods for Physicists, Afghan, second one, is very well-known book in the field of mathematical physics. This you can, of course, keep again. This is very important book. Afghan. This covers, I mean, this is has almost all the topics. It's just that, okay, we'll see that how when we proceed, if there are certain topics which are not here, then how to tackle that. And then the third book is Krizik, which is Advanced Engineering Mathematics. So generally, Afghan and Balakrishnan are reasonable. But Krizik, of course, I mean, there is no dearth of books in this particular area. Krizik is considered another good text in terms of application. As the name suggests, Advanced Engineering Mathematics, where it is more of the application side. So we basically have these 3 books written here. But time and again, we will keep on telling you some other books. Yeah. So this is about it. That these are 4 broad units. How the lectures are basically delivered in the department, you may have heard in quantum mechanics course theory lecture. One, that there is a theory teacher who takes lectures on 3 days, Monday, Tuesday, Wednesday for us, 10 a.m. to 11 a.m. So I have made the Teams account accordingly, right? Now then there is a tutorial. For each of this group, P2, P3, P4 or P1, there is dedicated session of the tutorial. We have a team of 4 people who is teaching this course. So I myself am there. Then there is somebody called Dr. Abhas, who is going to take care of it in the other class, which means for P1, P4 batches, the core theory paper will be taught by Dr. Abbas. And then there are 2 tutorial teachers, Dr. Tripurari and Dr. Neelam. These guys will take the tutorial mostly together, or we'll see how it goes. But generally, when the theory classes start, tutorial starts almost 1 week later. So tutorial classes should start next week. Anyway, there may be an introductory class. So please keep an eye on the mails which you get. So this is about how this course is basically taught. It is for teachers, one for you and two in the tutorial sessions. How the units are organized in it. Evaluation of the course is such that we will have a midterm internal assessment, which carries 30% of the weightage. And then there will be 70% weightage, which will be given for the final examination. So midterm internal assessment exam cannot be repeated. This is one important thing. So you have to ensure that when you are going to study, you won't be able to repeat your internal assessment. Even if you want to repeat your mathematical physics paper, you cannot. So out of 30, whatever marks are given to you, those marks will remain with you. It is out of 70 when you repeat the paper, let's say sometimes later, then those numbers can get changed. So it is important for me to tell you so that you can understand the this emphasis on internal assessment. Now it's mathematical physics course, so we are mainly relying on applications. That means we are interested in understanding the concept first, but then we would like to apply it. So most of the paper, I mean, whether it is an internal assessment, whether it is the final examination, it is composed of questions which have to be attempted. It does not generally include too much of the subjective one. The concepts may be asked, for example, in certain cases, but the paper is quite applied, which means, I mean, at some point of time, I will also share the final paper, which is given at least last year to these students. With this introduction, I would like to just take a pause and let you ask questions. Let you ask questions on these aspects before I proceed further.
So,
Yes.
sir, do we have all the 30 numbers for the exam, or it takes some teachers also? Teachers also taking
See,
some.
there are two items which are associated. One item is what we call as the assignments. So in the tutorial, we generally give assignments and we expect you to submit the assignments. That means, of course, after working it out. So sometimes part of the weightage is also given to those assignments which are submitted by you. Fine. Most of the time we have seen that it is 30 marks which are being given to your internal assessment examination which we take. But you understand that in the online medium, we also want to see how students are performing. And since there is no way to be in touch with them physically, so this is one way we have found that some of the teachers in certain groups also use the assignments. And that depends on your performance. We will distribute you the assignment sheets. We'll see how many of you are attempting things. If we find that you are not getting serious on it, then we may assign it. As the name suggests, it is internal assessment. It is subject to our understanding of how you guys are performing. So it may carry some marks. But at this point of time, we haven't yet defined. It will be on the basis of how you guys are going to perform in this class. So does this answer your question?
And sir, in the tutorials, do we have all the P2, P3 batch, or we have divided like in the labs A and B groups?
No, no, it is P1 batch completely, P2 batch completely, P3. I mean, you can see from the timetable, right? There is no P1A, P2B, A. In the labs, since the physical labs have limitations in terms of the number of experiments which we can have, so we have divided it. In principle, in tutorials also we'll have to do it at some point of time. But you also understand that we are limited in terms of faculty members or faculty strength. It's almost half. Uh, okay, so this Archana has been repeatedly entering, exiting. I do not know what to do. This, yeah, but okay. So we do not have further subgroups in the tutorials.
Sir,
Yes.
so any idea when we are going to have our IAs? I mean, A day.
You will come to know of it. Let's just take, I mean, it's 22 minutes. Let's just, where you will come to know of it. It is not about any idea. It is about the department has a proper committee. The committee decides it, and as soon as it decides it, it will be uploaded on the website. So it's not about whether it is hidden or whether it is already decided and not communicated. It will be soon communicated to you all.
All right.
Sir,
Good.
in the internal assessment part, is there any weightage given to the attendance also?
Attendance is what could be in terms of submission of your assignments, and depending on how you guys are basically doing it. I mean, in case if we do not see attendance in the class, we'll have to maybe do that, something like that. But at this point of time, we haven't decided on it.
Okay, sir.
Yeah, good. So, I mean, now that we are here, so let's just try to start with what is this syllabus all about? Why do we have syllabus like this, in which there are 4 units, and that has something to do with the development of physics. So, we started, let's say, long back, although in physics, but let's say the classical mechanics, particularly the Newtonian mechanics, that is started somewhere in 1700s or 1600s, I should say, rather say. And that basically was kind of the start of our classical mechanics era. In fact, till we came to, of course, 1900, we were almost all the time under the impression that classical mechanics is the only important one. And this explains everything, which over the period of time we realize is not true after particularly going through this quantum mechanics thing. But what was there in the classical mechanics was one interesting thing. And at this point of time, I just wanted to ask it from you. Does somebody remember second law of motion? Newton's second law of motion.
Momentum proportional to rate of change. Sorry, the
So
rate of
in
change.
terms of the
Force,
equation, can you just ask me to write it?
the
F
force is
equals to A.
proportional to
F
dp
is
by
equal
dt.
to M.
Okay,
Momentum.
force is equal to
M.
ma, or you can think of it in terms of where m is the mass, a being the acceleration. So we can also think about it in this way: m in one dimensional, m d square x over dt square, where d square x over dt square, of course, is the acceleration in the one dimension, is equal to the force applied, can be equated to the rate change of the potential energy as well, right? As soon as you look into this, what does this equation tell you? What does this equation tell you?
It is a differential equation of second order and first order in a potential.
Okay, so and what about the physical inference?
So it can be expressed as a gradient.
Yeah, fine. But what is the physical significance of this equation?
Force is conservative.
Energy with respect to position.
No, I mean, well, let's not worry about this part, whether the conservative or not. Let's just think about this. F is
So
equal to
if
m.
we apply a force, then body will be moved.
Right. When you solve this second order differential equation, what will be the solution?
It will be containing x and means linear equation means
To
equation
give
of
us
the
the
Ultimately,
position
you
of the
are going
particle.
to solve it.
F equals
Ultimately,
to
you are
A
going to
sine.
solve.
A time
Yeah.
dependent equation will come out.
Right. And by the way, in order to solve this second order differential equation, what is the minimum criteria that you will be able to get the
At least
solution?
two boundary conditions.
two boundary conditions.
Two boundary
Either the boundary
conditions.
conditions or the initial conditions, right? I mean, generally, the way we understood it, that if we do x t and x dot t is nothing but dx over dt, which we call as the velocity, for example, that instantaneous xt and x dot t being given as the initial condition, we should be able to solve the second order differential equation to get the time evolution of xt as well as x dot t. This is the starting point of the classical mechanics. You will see in the classical mechanics class that Newtonian mechanics ultimately leads us to a Lagrangian and something what we call as the Hamiltonian. Right now, I'm not going to talk about it, but an important thing which comes out of it is this, that if I want to know the state of a particle at any time, so state of the particle, then all I am supposed to do is to know the xt and pt, where p is related with velocity. I mean, you remember that in two-dimensional phase space. Why am I introducing this thing? This thing is introduced to tell you something interesting. One, the whole idea of what we call as calculus, that got introduced because of this Newton's law. Be it the differential calculus, see, it is a second order differential equation, so you'll have to solve it. So you'll have to figure out some methods of solving it. So we need to have the idea of the differential calculus. Or look at the right hand side, f is equal to minus del v over del x, which means if I want to get, let's say, v in terms of f, then I'm going to have an integral equation. Or for example, finding out the work done, kinetic energy. So the whole branch of this mathematics called calculus, differential or integral, it came in existence, or the development took place because of this important physics of the classical mechanics. And it led to the point where we understood that if we want to understand the state of the particle, which we call as, let's say that if we know about it at this point of time, we understand how it is going to ultimately evolve when we solve this second order differential equation. So state is completely defined by characterizing only two, x and p. If it is about a two-dimensional particle, of course, xy, px, py. If it is about the three-dimensional particle, it is x, y, z, px, py, pz. So state of the particle in one dimension completely defined by these two quantities, xt and pt. And the time evolution of that is given by this famous equation. You will see in the classical mechanics class that we will do the, I mean, you can write it in terms of Hamiltonian and you will get something like Euler-Lagrange equation, etc. But overall, the picture is rather clear. Now, what happened in 1900 so that the situation changed tremendously? What happened in 1900 was the famous experiment. So, can somebody remind me how quantum mechanics came into existence? Just the anything which you remember.
So through black body radiation.
So energy spectra of the black body radiation.
Yes, sir.
Excellent, excellent. Energy spectrum of the black body radiation. If you would try to explain that, you are unable to do it in terms of the classical laws. Planck did that something and came up with the famous Planck constant. And we also use, of course, the reduced Planck constant, right?
And sir, I think there is a story, Max
Yeah,
Planck
let's.
and Planck.
Yeah. We will see it in the quantum mechanics class as well. But here I would just say the major picture changed in terms of the state of the particle. So if I have to now define a state of the particle in quantum mechanics, how to define that? Can I even measure x and p simultaneously with arbitrary precision?
No, we can't.
Because
In
of the
case of
famous.
quantum.
Yeah, in
Heisenberg
case of
law.
quantum mechanics,
Heisenberg
Principle.
very good, very good. So you understand that x and p, which were well-defined quantities there in the case of classical mechanics, cannot be even measured simultaneously in quantum mechanics. And please see that classical mechanics was failing to explain some phenomena. So it is not that in the domain of quantum mechanics, it is that the quantum mechanics is the correct theory, and classical mechanics is a good approximation for macroscopic bodies. But let's come to this point, state of the particle, which was described by xt and pt in two-dimensional space. How do we define it? What defines the state of the particle?
Sir, wave function.
Through wave functions.
Right. Thank you. So this quantity psi xt defines the wave function which defines the state of the particle. But this guy, I mean, this wave function is quite interesting, and it is not what we are talking about in two-dimensional phase space. This guy lives in something what we call as Hilbert space. Now, this is sounding interesting, that we are talking about not only that the X and P no longer describes the state of the particle. It is the wave function, one. And X and P were in the phase space where we have to only think about two dimension, X and Px, and we just draw trajectory there. But now we have to think when this wave function, where this wave function lives actually, it lives in something what we call as the Hilbert space. Anyway, so we'll come to Hilbert space later. But how do I know the time evolution, by the way? If I want to know the time evolution, just like there we solved the Newton's second equation.
Through the Schrodinger equation.
Right.
Independent Schrodinger equation.
So
Schrodinger's time
non-relativistic
dependent equation.
spin zero is given by Schrodinger equation. So you can speak out and I will just write down H psi xt is equal to,
Ishai.
Isha.
yeah, E psi it won't
Psi.
always, E psi it won't always be, you see that, and I will also little bit say it here in this class. And this H is called the famous Hamiltonian or Hamiltonian
Minus
operator, and del square over del x square plus Vxt. So let me just explicitly write down the whole of it. So let me explain. I have written it down, and in case this potential guy does not depend upon time, then you can do the separation of variable for the wave function. You can write down your xi xt as the product of phi x times some chi t, and then you can solve the first equation, which we call, I mean, let's say the equation of state or time evolution. Then you can solve this, the H psi, to get this E psi, where E will be the energy and the constant of motion. Right. So basically, what has happened in quantum mechanics, interestingly, that in case if we want to measure a quantity or there is a physical observable, then we first get something what we call as operator. We operate it on our wave function. So we operate this operator on the wave function and get some results in terms of what we call as the eigenvalue equation. Okay, too many things together. You have done that. I'm just saying it, but we'll see. So time independent one will look something like this, where E is what you call as the energy, and H is the Hamiltonian operator corresponding to the energy. We of course identify it by having the two terms, the kinetic energy term and the potential energy term. Kinetic energy term is given by P square over 2m, which of course if momentum operator, which we call something, so is written like this. This is what you have done in your undergraduation. Remember, it is the non-relativistic spin zero particle. We are not talking about anything else. But what has this brought in the picture? One, that this psi was living in the Hilbert space. Okay. Two, there is something which is built in the quantum mechanics, which is this I. What is this I?
It's a complex number, root over minus 1.
complex
Root
number
over minus.
iota.
What
Under the
about
root
the
minus
psi xt itself? Is it a real number? It's a complex function or what?
A
This
complex
can
So
be
it's a complex function.
Can be
complex
complex.
function.
complex.
Can be a
So
complex.
psi xt, psi x itself is real, but psi can be a complex number as well, right? So one thing which clearly comes out, complex number is inbuilt into this quantum mechanics. If you have to solve this equation, which corresponds to, let's say, the Newton's second law of equation, which we saw in the previous page, then we have to have one I, which is the complex number inbuilt. Psi xt, we will get the solution in terms of the complex number, which is also implicit. But we'll have to now think about complex numbers. And hence, in your course, this unit 3 is about the complex analysis. The unit 3 is complex analysis. Why it is there? Quantum mechanics changed the way we were doing mechanics. Since it relies on solving this kind of a problem where we can have these complex numbers, so we'll have to expand the scope in terms of complex one, and hence your unit 3 is complex analysis. Good. Now what about unit 2? It is about probability and statistics. So let's just see what it is there in terms of the interpretation of xi xt. So if I want to measure xi, It's a complex number. I cannot measure it. So what is the physical interpretation of psi?
So physically, we
So
can
if we
interpret
take
psi
the
square as the
Entire probability is 1.
So
density.
the
I have no physical
the
significance.
complex of psi and
Sir,
psi
Right.
square
All of you are
square.
the
absolutely
probability of finding a particle psi itself cannot be expressed, but psi square gives the probability density according to the Copenhagen
right.
interpretation.
Almost all of you
Yes.
are saying, but this is the famous Max Born who gave this interpretation. Please remember this name because the name is very important. Anyway, psi x, the way you are saying it, let me just put t also, mod square dx is the probability of finding the particle in x and x plus dx. And in order to put this as the probability mod psi square, there is another thing which we'll have to remember, that the normalization of this psi has to be, just like you
One.
said, this has to be
One.
equal to 1, so that it gets the total probability of finding the particle anywhere in space has to be unity. So this interpretation came from Born, but as soon as this interpretation came, you understood that we are talking about psi, which gives you the probabilistic, having the probabilistic interpretation in terms of mod psi square. And unless we talk about the statistical properties, we cannot even think about how this psi is going to behave. So let's just go back to what I said, double slit experiment with electrons. So the famous double slit experiment with electron, if I send one electron through the double slit, then what do you think that it is going to, where it is going to arrive on the screen, which is, let's say, at a far off place? Can you
So
tell
it
a
is going.
priori? Yeah.
So it can give. It will give a pattern of interference. It will give the
No, but
interference
I am talking
pattern.
about one single electron.
So we can't
The
determine it.
50-50 chance for both the slits.
There will be a region where it can.
So
No,
this
I'm
proves
see,
that.
you have
There's no
actually given
particular
me the
reason.
interpretation, but I'm
Yes.
asking a very simple question. A single electron, when passes through this double slit, where it is supposed to arrive at the screen? Can you tell me a prior?
I think no interference pattern.
No, I don't think we can.
No, a
So it
single
will behave
electron
like a simple
cannot.
particle.
Remember,
So no,
There's
it.
remember
no particular.
So it will
from
behave
the
like a
No particular.
wave.
yeah, from but on the screen
We
you
can
will see a wave. On the screen you are going to see a single particle being detected.
A single
So
particle.
we're going to see a
Uh,
single
You see a
particle
wave.
being
One single
detected.
single particle.
particle just
Right.
behind the slit.
So there will
A
be
wave.
a flash of light at a single point somewhere on the screen. Once you detect, remember this electron, famous collapse of the wave function to that point. Yeah. But the interesting thing is, if I keep on sending electrons one after another, then what you are going to observe after sufficient large collection of those electrons, that there is this interference pattern. So as if somehow, even though I cannot say anything about a single electron where it is going to be there, which gives us the probabilistic interpretation, but statistically we can still say that if there is a large collection of identical electrons being passing through this double slit, there will be some wave kind of pattern, which basically is coming from this psi called as the wave function. Remember this famous, this wave function, why do we call it? In fact, later on, we do not even call it wave function. I mean, although it's a common way, we call it a state vector, and I will come to that. But what I am trying to rely on right now, that there is something what is called the probabilistic and statistical interpretation. Hence, the syllabus unit 2 is about the probability and statistics. Since we are dealing in quantum mechanics with something what we call as the probabilistic wave function and corresponding statistical behavior of the particles together. Okay, so that is the reason why we have in this unit 2, probability in statistics. Now, unit 4, which is about the group theory, is mainly related with what we call as the symmetry operations, although you have already read a little bit of it, but I will mention about it later on also. when we reach the group theory, it is related with the symmetry operations, that when you are applying, for example, some sort of a potential, if there exists certain symmetries in this potential, then we can say certain things about the wave function without even solving these Schrodinger equation. So that is beautifully explained is what is called the group theory. So three things: complex analysis, it's built in the quantum mechanics; probability in the statistics, built in the quantum mechanics; symmetry operations, which is the group theory, is because we are able to actually explain certain properties just on the basis of the symmetry; and finally the linear vector space. This has something to do with what we are discussing here. Where does this wave function live? So unit 1, which is linear vector space, is somehow related with the concept. I mean, the Hilbert space is actually related with the concept of the linear vector space. We will soon see how it goes further. And that is why those 4 units are there: linear vector space, probability and statistics, complex analysis, and group theory. So questions here so that I can move forward and tell you something interesting. Oh, okay. So let's just go to the next point. Now tell me, I mean, this wave function xi is a complex number. You have already told me. If let's say xi1 is a solution of the Schrodinger equation and xi2 is also the solution of the Schrodinger equation, same Schrodinger equation, will be the solution of the Schrodinger equation?
Yes.
Yes.
Yes,
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 sir.
sir.
yes,
When we
yes.
need
What
a
are these
combination of
C's?
Yes,
What
sir.
are these C's?
Because Hamiltonian is a linear operator.
Yeah, so we'll come to that. I mean, you already know that. I do not even know what to do about it, because since you already know, what can we do? I mean, this is something clear. The important thing which we'll have to remember: C's are the complex coefficients, right? So these guys are the complex coefficients. We are not talking only about the real coefficients. This is called the famous principle of
Superposition.
superposition. Okay, tell me something else also, now that we are a little bit discussing about it. So psi xt is a wave function. If there exists another wave function, let's say psi2, which is c, such that mod of c square is equal to 1. So you can think about c can be something like e iota theta. So can you make a distinction between this psi1 and psi2? And what is this guy called theta?
I think if mod c square equals 1, so psi2 should be the solution for any particular time. That should be the solution which the Schrodinger equation should follow.
No, but I mean, you guys have see.
So it is
Okay, I mean,
only linear.
question is this: you yourself
With
said that any physical interpretation of xi is mod xi square, right? Or mod xi square dx or whatever. Any physical interpretation requires me that. Now I have given you psi2. So my question: mod psi1 square, is it same as mod psi2 square or different from it?
answer, yes, it is same.
It can be
It
the
It's
is
same.
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 Sir.
It is same. So it is physically indistinguishable
Yes,
in
it
terms
is
of the
dependent.
observables. This theta is called the phase, the famous phase. So what it says, that if basically if I multiply my wave function by any complex number which is such that mod psi square is equal to 1 or unit norm, then that wave function is indistinguishable, and that is what is about the phase. This is where the theta is a phase. So why do I make a big fuss about these complex coefficients, and I write C1 psi1 plus C2 psi2? Why shouldn't I simply write psi1 xt plus psi2 xt?
Sir, I think these coefficients tell us that what is the probability of finding the particle in that particular psi1 or in that particular state of psi2.
Okay, anybody else? Yeah, okay. You already know quantum
they
mechanics, so
are
you are
to
able to
provide a
explain that.
more complete solution.
You have to, there
So
it is
they can
providing the,
encompass any possible state.
right. Okay, I mean, I am not going to dwell on this topic further, but please see that even though psi1 and psi2 are physically indistinguishable, let's say. But if I make a state like psi1 plus psi2, where you have this psi xt plus ei theta times psi xt, suddenly you will see that in case if you are going to take mod square, then this ei theta will not disappear, or the phase will not disappear, and this will give you the famous double slit interference pattern. Anyway, what do I wanted to say from that? It tells me that whichever space my wave function, which is a complex number, is living, somehow I should be able to multiply it by a complex coefficient, and I should be able to add it also with each other, the complex numbers, so that I get the resultant solution, which is still the solution of the Schrodinger equation. So that means I should be able to play with this wave function at least in terms of two things. One, I should be able to add them, and two, I should be able to multiply it with some complex numbers. So those two are inbuilt in it. And here comes my famous introduction of what we call as linear vector space, which we call as LVS. Now, what is
Very.
hello?
Yes, sir.
You are saying something?
No, sir.
Okay, yeah, kindly mute. Okay, so linear vector space. Why this concept? This is a general concept in order to understand that where my wave function lives for our physics purposes. But this is a very generic concept in mathematics. The whole idea of extending or using the linear vector space in quantum mechanics comes because our mechanics changed from this XTPT to the wave function, which itself is a complex number, which has a property of the principle of superposition, things like those. So what is linear vector space? Now, in terms of mathematics, linear vector space is nothing but set of, or a non-empty set of elements which we call as vectors. So we use something like u, v, w, and you see that I am using something like this to define that these are called vectors. It is just, I have used this one because famous Dirac used this notation, and you will be utilizing this notation later on in your quantum mechanics class. But it is something similar to when we say this guy or this guy is a three-dimensional vector. So why do we put an arrow on top of it? It is just to remember that we are talking about three-dimensional vector space. I am giving this notation to generalize from three-dimensional vector space to something where we will still call them vectors, but no longer just the three-dimensional vector. So I'm talking about linear vector space. It is nothing but the set of elements which are called vectors, and together with field of scalars. Now scalars, when I am saying, these are the either real numbers or complex number for our case. And I will define this alpha, beta, gamma, so on and so forth. So what is linear vector space? We are defining. It is nothing but a set or non-empty set of elements, which we call as vectors. Together with field of scalars, it obeys law of vector addition and scalar multiplication. Okay, so I am defining my vector space. We need to have our set of elements, which we call as vectors, which together with the field of scalars will obey this law of vector addition and scalar multiplication. What are those laws of vector addition and scalar multiplication? So I will define this vector addition as this plus, and I will define this scalar multiplication as this dot. So what I am going to do, any addition of, okay, I should write down, any addition of the vectors, if I am going to do vector addition, if I am going to do, this will belong to the same vector space in which my original vectors are there. So this set of element vectors which constitute this vector space. So if I am going to add them, u plus v, using my rule of vector addition, then it will still be in the same space. Okay. What are the other rules? U plus v plus w will be equal to u plus v. Now what is this famously called? Law of
Associative law.
Associativity.
association or associative, right?
Yes.
Then, so this is, let me 1, 2, 3. There exists zero vector in this vector space. So in this vector space, there exists a zero vector such that if that vector is added to my original vector, my result is same. So it is not going to change the original vector. 3. This says the property is famously called the existence of unique null or zero vector. 4th, there exists another vector which I am defining as the inverse vector, which when added to my original vector is going to give me zero vector. And finally, 5th, that if these are there, then this guy is commutative. I will tell you why these properties, how these properties are useful. But at this point of time, I have told you 5 properties. This is the famous one, u plus v, v plus is equal to v plus u. This is called
Commutator.
commutative.
Commutative relation.
Yeah, commutative property. Yeah. Okay. Now, these were about the vector addition. Let's just do something about the scalar multiplication. If this vector is multiplied by a scalar, remember my alpha, beta, gamma, they were either the real numbers or the complex numbers. So alpha dot u. So if I take a product of this, then this still belongs to the same vector space. So addition of the vector. So if I am going to do the addition of these vectors, then it is remaining in this space. And if I am multiplying any vector with any scalar, then that also remains in the same space. Okay. This is, by the way, this is something what we call as the closure. Okay.
So,
7. Yes.
so what is the difference in linear vector space and Hilbert space?
There will be plenty of difference that we will come. I mean, I am starting with the basics right now. Fine. Yeah, we will see that. See, how do you, if I have to, let's say, if I have to ask you, you have to just climb a staircase of 100 stairs. How will you start?
From the first, sir.
Great. So that answers your question. So what we are doing, we are now basically going to have our concepts clear so that in the end we will be able to discuss this Hilbert space. In order to understand this Hilbert space, this is to be done. But one thing is sure, Hilbert space is a linear vector space surely. It will have some more properties, but it is a linear vector space. And that's why we are reading it. Good.
Oh,
So,
okay, sir.
so does this answer this portion? Okay, let me just write down a few more things so that you see that this is called the distributive property. Another distribution is with respect to scalar multiplication, alpha plus beta. This will be alpha u plus beta u. Okay, property number 9. So I am still going ahead with my properties. Alpha dot beta dot this. This guy will be equal to alpha beta dot u. And final property I would like to write 1 dot u, this is 1 is a scalar now, is equal to this u. Now, please see why I am using this interesting notation of plus for the vector addition. See,
So
I
in the
have,
eighth point, you missed the beta part.
no, I haven't. Oh, this one, sorry, this guy, alpha u plus beta u. Actually, I haven't, but the way I have written it is like this. Can you now
Oh,
make
okay, okay, got it,
yeah?
got it.
Yeah, sorry for that. Yeah, because this guy is actually interfering mathematical physics one. Anyway, see that I will of course tell you several things about it. But one thing which you can quickly see, when I am doing vector addition, I am using this plus with this circle. Whereas when I'm doing my scalar addition, alpha plus beta, it is, I mean, either the real numbers are added or the complex number are added. So this plus sign doesn't make any distinction. This plus sign is the regular plus sign which you are always using. On the other hand, for the vector addition, I will have to first define the rule and then only you will do that. Okay. So let me just tell you what these properties are. One, that it has to have a closure under vector addition and scalar multiplication. So there are two closures. Second, of course, is the associative law. Third is the existence of null vector. Fourth is the existence of inverse. Fifth is that the law is commutative under vector addition. And then rest of the properties are more on the scalar multiplication. That this scalar multiplication, of course, gives the closure. It is distributive both with respect to vector addition as well as the scalar addition. So these two laws just tells you that. And then, yeah, so I should write alpha dot so alpha dot u, alpha dot v, beta dot u, beta dot u. Then the alpha dot beta times u is alpha beta times 1 u. This is famous associative property of the product or the multiplication. And then there exists something called 1 scalar 1, which when multiplied with u, I mean this vector, gives you the same vector. Now, what do we call this? This is basically called something like algebraic structures. Remember, if I ask you, what about the three-dimensional vector space R? Does three-dimensional vector space, vectors which are staying in the three-dimensional vector space, do they follow all these properties? So let me ask you this way. So if let's say R1 and R2 are the two vectors which belongs to my, so R cube, just to tell you that it is a three-dimensional space where R1 is vector in x, y, z or something like that. Yeah. So do these follow all the properties which I have written here? Does the R1 vector plus
Yes,
R2 vector, that is another vector in the same vector space?
Yes, sir.
R1 plus R2 plus R3 vector, is this associative?
Yes, sir.
Yes, sir.
Yes,
Does
sir.
there
Yes,
exist
sir.
Sir.
zero vector? Yes.
Yes, sir.
What
Yes,
Yes,
about
sir.
sir.
the scalar multiplication?
we just
If you
Yes, sir.
multiply
It does
it's
follow.
a
vector,
vector in R3, sir.
three-dimensional vector with a number,
Yes, sir, it follows.
will it still be a vector?
Yes.
Yes, sir.
Yes, sir.
Except that you will tell me, sir, it is a vector. However, it is a vector space. Sir, you should be defining only in terms of scalar multiplication by a real number.
Hmm.
Yes, sir.
So that the three-dimensional famous vector space, when I talk about another vector, it is 5r. I do not generally talk about 5 plus ir, right? So three-dimensional vector space is a vector space of vectors like this, along with the scalars, which are real numbers, which obey two laws of one vector addition and scalar multiplication. So let me just write down now. If I have to write down my vector space, then what do I generally write? I basically need to remember it. So I define it like this. It is a vector space over a field, which is field could be a real number or a complex number for us. having defined the rule of vector addition and scalar multiplication. So this guy is a triplet of algebraic structure, such that the purpose of this guy vector addition is when I multiply one vector with another vector, this is a notation which is a famous mathematical notation, it remains in the same vector space. This is what we call as the closure. Or if we multiply a scalar with the vector space, then also we remain in this one. So this guy deals with here. We will take plenty of examples just to see that we understand it. Although I understand that those who have done physics honors from Delhi University, they had some course on the linear vector space somewhere. So at this point, I will just ask for the questions because it is 11:01 and I do not want to extend beyond another 3 minutes. So questions related with this. I'm going to post my scrapbook anyway on the website. I'm also going to post the video also. But questions for what we have done about the formal definition of the vector space. Tomorrow we'll do examples and do something else. Set of elements which we call as vectors together with the field of scalars which can be real or complex number. Always law of vector addition and scalar multiplication, which are 10 in number. The book which I will surely subscribe you or tell you to please look into, the something which is also called in given in your quantum mechanics class by R. Shankar, Principles of Quantum Mechanics. Very nicely written book. First chapter is about this one. Anyway, questions related with it.
Sir?
Yes.
Sir, I have read this linear vector space in my 5th semester undergraduate program.
Yes,
but
sure.
But the symbols that you used are a bit tricky. So can you please give it a minute?
Yeah. No. I mean, that's good. One, uh, I will have to explain why I'm using this plus kind of a symbol in this circle for vector addition and not any general plus. Yeah, that is one thing, right? Symbol for this guy for vector is basically used to distinguish it. If I generally write, let's say alpha or alpha like this, how will you decide whether this is a scalar I am talking about or a vector? So why did you invent a symbol like this, something which is something on the head with the arrow sign? What does it signify?
Vector is a vector.
Vector. Yeah. So, but this is a one example, three-dimensional vector, right? Nothing beyond that. When you look at our arrow, it means that you are talking about a point in three-dimensional space, right? Tomorrow when I will give you examples, or next time when I am going to give you examples, you will see that this is just one example for my vector space. So I have to just give some notation. The notation which I have given for this vector, I mean, I could have used anything. I could have simply said u is a vector, fine. But then you'll have to keep on remembering that this u when sir is talking about is a vector and this alpha when sir is talking about is a scalar. So I had to somehow distinguish it from my scalars and I have used a notation which was given by famous Dirac. Fine. It is actually called ket and I will also explain that. But for you at present, it is just a symbol to define vector. So if I am now, let's say I am adding u plus v, how do you know that I am not adding scalars? As soon as I write this, what will you call this?
Vector. A vector.
Vector addition or scalar addition? Yeah.
Vector
So
addition.
in order for you to remember that it is a vector and not a scale. I mean, I am going to give examples. Still, I give you examples. Of course, it will keep the life a little bit difficult. But when I give the examples, then you will understand why I need to generalize the notation, which was used as this R vector all the time. Yeah. One thing you are clear that we cannot live in real vector spaces because we are going to deal with complex one. And I am pretty sure at this time you understand why I want u plus v to be in my vector space and alpha times u to be in the vector space because of the same reason that we discussed this guy wave function. Remember the principle of superposition? This also is the wave function which is the solution of the Schrodinger equation. So if xi1 xt is identified as u, xi2 xt is identified v, alpha is identified as the complex coefficients, then by saying that in the vector spaces all the vector addition and the scalar multiplication vectors also live in the same space, we are basically trying to explain that the principle of superposition will still hold true in my vector spaces. And that is the reason why actually we use vector spaces. In fact, this is the reason why we call it linear vector spaces, because it is the linear principle of superposition what we are using. Any other question? I mean, that was a good question. Yeah.
All right, sir. Thank you.
Can you repeat this point where you
Oh.
told that you'll use this plus with a circle in case of vectors and just a addition sign in
See,
case
I
of
mean,
scale?
the way it is, I will give you examples and that will help us, but the time is short, so I cannot give the examples right now. So if I write like this, see, I can still write it. And you can say, sir, since you have written two vectors, so it is vector addition. But let me ask you in three-dimensional space. If I give you number 1, 2, 3 in some basis plus 4, 5, 6, how will you add those? Vector, three-dimensional vector. How do you add those?
The first one added to the first 5,
Yes.
7,
Individually
9.
adding the coordinates.
Right. Now you have defined the rule that this guy has to be added to this guy has to be added to this guy has to be added to this, right? It's not how the numbers generally add. I mean, numbers can be added also, 1 can be added to 5 also. So basically you have defined a rule for this addition. This is what we are talking about when we are defining a rule that the first guy will add with first, second will add with second, third is added with third. It is more than just a sum of the real numbers. It is a rule that you are defining that whenever number like these three come in parenthesis, we will be adding the component wise addition. This is what we call, right? You got the point?
Yes.
See, 1 plus 4 is always 5. That you will always write. But who told you to write 1, 2, 3 in parentheses to be added like only in the component? Somebody as a rule. And that is why I'm saying that we are adding vectors. Then there is this rule. If these are complex number, 1 plus I plus 3 plus 2I, this rule is just the addition. Normal law of addition. 1 plus 3 is 4. This is what you call as 3I, and then it is done. You are done with this thing. But here you have to define this rule. And that is why I'm using this concept of this plus. By the way, I'll have to end the class. Otherwise, the next teacher will not leave me. So, okay. So guys, we will give enough examples to see that why I'm calling these notations, why I'm using this, and we'll see it. And we'll have to, of course, take it to the Hilbert space, but that will be done later when we take this steps. Yes.